Our next speaker is Daniel Andrés Díaz-Pachón. He's from Miami here, and he will talk about the formal framework on learning and knowledge acquisition. Thank you.
Thank you. Well, thank you for the invitation. Yeah, well, that's the title of my talk. This is joint work with Ola Holger from the Department of Mathematics at Stockholm University. Jason Rao, who was the former division of the director of the division of statistics here at the University of Miami, and he is now at Minnesota. And Calvin Matthew, bright high school student who has collaborated with me in some papers, with one that we already published and some others we're planning. Okay, so this problem is inspired a lot by philosophy, and I really like philosophy in epistemology, basically. Philosophers usually distinguish between three types of knowledge. The first is acquaintance knowledge, which is just to get to know a person. And if you think about it, that problem is one of the most popular topics around in math in terms of networks. There are lots of references that I could use for that. There is another type of knowledge that philosophers talk about, that is knowing how. And knowing how is know-how, learn skills. And that is usually also well measured in terms of psychometry, and classical statistics was partially involved in that direction. The third one, knowledge that, is knowledge about propositions or facts. And that is not much covered, and that's why with my collaborators we went to develop this direction. We are going to use, as you will see, a combination of a frequent instantiation approach, which is kind of interesting because those things tend to be mixed much in the literature. So before going to the mathematical formulation, let me explain what is it that philosophers refer as knowledge. They say that knowledge is a justified true belief. That's how they put it. So then, basically, the definition has three parts. It's a belief. An agent A has a belief in some statement S. Then the true belief requires that S is true. And the third part is that the belief is justified.
What's the difference between the last one and the...
I will go very in a lot of detail about that, so I will answer you. So again, that's why they call it justified true belief. Now, if only the first two conditions are satisfied, we will say that actually the agent just learns this statement. So learning is a true belief, and knowledge is a justified true belief. So in sense of those requirements, the knowledge is more constrained than learning and more constrained than belief. And put in that sense, then we can develop some apparatus in terms of, first, here for belief, we can use the classical notion in Bayesian statistics that probability is a belief. And then for learning, we are going to use information theory to define learning. And knowledge, we're going to impose some other restrictions that we will see. One thing to mention here is that all these inclusions here are actually proper. That means that it's possible to have a belief in a false proposition. That happens a lot. And it is also possible to learn something without getting to know that something, so without any justification. I mean, intuitively, at least before the formal mathematization, it makes sense to have those things as proper inclusions. So let me give you an example that I'm going to use repeatedly during the talk. So suppose that the agent A is a teacher. And the teacher gives the student a student's home assignment test with double choice answers, one right and one wrong. This is, of course, just made so that writing the math is easy for the example. So the teacher is interested in the proposition, the child is expected to score well on the test. So the space of possible answers, or the possible results for that proposition are three in our situation. Three, the first one is going to mean actually that the student does not do well in the test. But let's say that the student does well in the test, actually. But in the second case, for X2, the student did it by himself. And in the third case, he just received a little bit of help from some friend or something. Then, for this particular statement, the child is expected to score well on the test. We're going to have that actually this answers, the options X2 and X3 are actually sufficient to learn that proposition. In general, if the student answers substantially more questions right than wrong, then the teacher learns S. Again, this is just an opening. We're going to formalize all these things later. However, if we set a different proposition or statement, the student knows how to add. It is not enough knowing A to determine if actually the student knows how to do it. So selecting this set as it is enough to learn that the student is scored well on the test, but not that the student knows how to add. So, of course, as it's common in statistics, the more questions the test has, well, the more certainty the teacher is going to learn about, is going to get about the learning of the student. Now, let's say that if the student is monitored during the homework, then the teacher can learn the second proposition. So let me give you a background on this space because this is going to be really important. In this talk, I once read one quote by Peter Medawar, and he was saying that many times it is not as important to develop new things as to find new ways to use tools that are already developed. And I think a lot of what I'm going to say here is going in that direction. So in order to understand a lot of the concepts, we're going deeply in many of the foundations of probability and statistics. So we're going to consider XF, a space of possible worlds, which is going to be values of a parameter, as it's usually done in statistics. So you can think of a model, and then those possible values of the parameter are your space of possible worlds, where F is the biggest sigma algebra that you can think of for that space. So if X is discrete, then your sigma algebra is going to be the set of parts, and if X is continuous, then it is going to be the world sigma algebra. Now, we're going to make a frequentist assumption, and it is that there is a true world. There is a true value of the parameter. In the real world, the parameter has actually some value. This is a frequentist assumption because that is not usually done by Bayesians. Now, the rest of the worlds in this space are going to be counterfactual. Now, S is going to be a statement that can take only two values. It can be either true or false, depending on the word X. And that is going to be measured according to a truth function that is just taking binary values. In the end, this F can be taken as the physical probability of what is happening in the real world. Just this statement is true or this statement is not true. So it's going to be either 1 or 0. So that F is actually a probability measure. So A is going to represent the set of words in which the proposition is true. So that is totally defined by the function F. Whatever F is 1, then I'm going to consider that as an element of my set A. Now, beliefs, that's for the space. For beliefs, we are going to consider now a Bayesian approach. We're going to have a space, a probability space, with some distribution or some probability measure P0 representing the beliefs of an ignorant agent. That P is usually going to be in the state of maximum entropy given the restrictions that we have. If the space is finite, then that P is going to be uniform in the assumption of maximal ignorance. On the other side, an agent A, not the ignorant one, but an agent A, is going to navigate this probability space with this different probability measure. And that probability measure is affected by additional information that the agent A has acquired. So notice that our assumptions for the ignorant agent and the agent A with some additional information are Bayesian. That means then that in all this setting, the agent is updating his beliefs or her beliefs according to a Bayesian principle, whereas reality, let's say kind of ontologically, what is happening is actually a frequentist assumption of a real world. That is basically how the system works. So that probability is just going to be a posterior probability of with prior the distribution of the ignorant agent and likelihood according to the data. The interpretation that we're going to give to this P0 and this P, the probability measures of the ignorant agent and the agent A respectively, is that they are their prediction of the physical probability of X0, what is happening in the real world. Okay? That's the kind of thing that we are using here. So P0A and PA measure the belief they have in what is happening in the real world. Now, when we're setting this sigma algebra G here, we're going to go into something that we are going to call the discernment. So sigma algebras in our case are going to represent discernment. How much can we go into the space, or how fine can we go into the space according to the information that we possess? So for instance, for the agent A, we assume that the data is giving the agent some kind of additional information that is going beyond that of the discernment of the ignorant individual or the ignorant agent, and it's contained in the maximal sigma algebra that we assume at the beginning. Now, the point is, however, that the agent A does not have any additional knowledge beyond this sigma algebra than the ignorant agent. So beyond, for events that are not included in the sigma algebra, he's simply going to assign the expected value of the event, which is exactly the same thing that an ignorant agent would be doing. So beyond that level of graining that is provided by the sigma algebra, then the agent with additional information is behaving exactly in the same way as an ignorant agent. So that means that G is the maximal possible discernment that the agent has. And the agent cannot go beyond that level of discernment. That then sets what is exactly the posterior probability or the belief of the agent A. The belief of the agent A, just by definition, is going to be the expected value of the truth function. Remember that it was a 0-1 function. But that value of the function is basically just the conditional expectation of f given the sigma algebra G. And then just by this condition here, we obtain the last equality, which is replacing the internal expected value. Now, if we have G, the sigma algebra G, which is the discernment of the agent A, and we have an unlimited abundance of data, unbiased, assuming that the data is unbiased, then the agent E is going to assign probabilities just according to basically indicator functions for all the events in that sigma algebra. That's what we mean. But then again, for events that are not in this sigma algebra, the agent is just going to take averages because he or she cannot do better. This is cool in case of unlimited amounts of data. But this is still limited if G is strictly contained in F. So whenever G is properly contained in the sigma algebra F, which is the largest sigma field, then the measure P is not going to be the same as a point mass evaluated at the true world, particularly, which is the one that there is something interest to us. In case that the agent is an oracle with maximal amount of knowledge, who also knows which is the true world, then in that case, the sigma algebra G is identical to the sigma algebra F, and because the oracle knows what is the true world, then P becomes a point mass at the true world. So notice that the difference between these and these that looks almost the same is only on the memberships of the sigma fields. In this case, basically for all singleton in the space, the agent can make a perfect assessment. In this case, the agent can only do the assessment for elements in that particular sigma algebra, which is more restricted. So let me continue with the example that I gave at the beginning. Suppose that the teacher assigns the homework with 10 questions, true and false. Then the data that the teacher has is just some random variable in this space of 0 to 10. And now we have a prior, which is the statement of maximal ignorance of 1/3. Remember that we have 3 possibilities. The student did not know, the student did well the homework, and the student did well with help. So the prior is going to be uniform. Now, the data, just by the assumptions that we are making, is just a binomial for each of the x's with some parameter pi sub I. In the case of the ignorant, in the case of maximum entropy, well, this is just going to be 0.5. And now, let's say that if the student scored well, then pi 2 and pi 3 are 0.8, where pi 2 and pi 3 are the proportion of good answers given that the student scored well on the test. So that gives us that, notice, the probability in the 2 cases, x2 and x3, is the same, just because the likelihoods are the same. The likelihoods only depend on the pi i's in the difference, but pi I is the same for 2 and 3, for I equals to 1 equals 3. So this, there's no way for the teacher to make a difference between these 2 situations. Let me continue with that example. The sigma field in that case is going to be, well, this simple thing is almost trivial sigma field. The empty set, the space, the event x1 that the student doesn't know, and the event that the student does well on the test, which is x2, x3. And the point of the example is to see that A cannot discern between the elements of X beyond what is given by this sigma field. He cannot do that better than an ignorant agent. So, to see this, just let's notice that this is, well, that actually there is no sigma field between this field and the sigma field of parts. Yeah.
Sorry, for the last example.
This is the same example.
No,
This
it's
is
the
the
same.
same.
The phi is the probabilities or what?
These pi's?
The nominal, yes, you have, yeah.
Yeah, these pi's are meta parameters that are given to the prior.
It's not a probability, I mean.
It's a probability because it's, let's say, the second parameter of a binomial, the probability of success of a binomial.
Okay, got
and it depends on the excess in the words, on the, we are considering as the word. So the student does not know, then basically he has a probability 1/2 of doing well in each of the questions. So for the first one, that's going to be 0.5. If the student knows, then he's going to have a higher chance of scoring well. That's the point. Now, coming back then to the situation, this is the sigma algebra that we have, and then we can see that between this sigma field and the sigma field f of the set of parts, there's actually no sigma field. So in order to see then that any measurable function is not going to be able to differentiate between those two, well, you just have to consider that g prime is the same as g. But then, in that case for g, a measurable real value function, then we have that the expectation of g, the conditional expectation of g, given the sigma algebra g, for the event xi is going to be just gx1, the value of the function for the first, in the first case, when the student does not do well. But in the second case, for the set A, it's going to be just the average of the two possibilities, because again, in the case of ignorance, we take the average. That's basically the situation. So, given that background, we define learning now in terms of information theory. Now, I have used this guy a lot in my own research. We call it active information. And it is an average version of the entropy, of the conditional entropy. But for some reason that I don't know well, most of the research on information theory has focused on averages. We take all the time entropies, we take all the time Kullback-Leibler divergence, we take all the time mutual information, and all those things are actually averages. Averages in L1, actually. Recently, I've seen some developments in L2 taking variances and using those variances, they call it var entropy, in order to calculate mixing times of Markov chains to the stationary distribution. Pretty good results. But it's only new. And it's very weird that in general, local measures of information are not considered. I don't know why. I have used this a lot, as I said. And then we are going to define learning actually using that, saying that there is learning if the statement is true in the true world, and the active information, so the logarithm of the posterior or the prior, is positive. Or there is learning if the statement is false in the true world and the active information is negative. So what we're saying is that actually the belief that I formed after getting some data is driving me closer to the direction of the true value. That's the point of the definition.
Wait, so this number P of A divided by P0 of A is not necessarily between 0 and 1.
Yeah, these two values are between 0 and 1, both. The quotient is not necessarily between 0 and 1, but each of those is, because each is on a probability distribution. So no, the quotient can be between 0 and infinity, basically.
It's not normalized.
No, it's not normalized. It's not normalized. And that's the point. That's one of the advantages actually of not using the average. Because you know, if you use the Kullback-Leibler divergence, the Kullback-Leibler divergence is always non-negative. That is the average of this value over all possible events or possible singletons. So the Kullback-Leibler divergence is the expected value of this thing. And that thing is always non-negative, which generates a lot of bias, among other things. This actually can tell us when this is negative that P is less probable than actually that A is less probable using P than P0.
Sorry, of course you explained that, but can you say one more time what's the difference? What is P of A and P0 of A?
So this P0 is the prior belief.
P0 is a prior belief.
P0 is the prior and P is the posterior. and A is the set of words in which the statement is true. Okay, that's it. So these things are the beliefs that the agent in the numerator A has about this proposition F, the statement S. And what is in the denominator is the belief that an ignorant agent has about the statement S that we made. Okay? Okay. Now, the point is that this is not enough. We can have biased beliefs. How so? For instance, suppose that my probability measure is supported in some set that excludes the true word. If that is happening, then that's represented in this figure here. So imagine that the set of words in which the proposition is true is this set A. Then, under the uniform distribution, which is the assumption that we are making for the ignorant agent, then you have this uniform probability for the event A. Now, the support of the posterior is represented by this black kind of histogram. So notice that the support is excluding what is happening in the true world. It's assigning 0 probability to the true world. Then in this case, actually the belief is biased even if all the belief is concentrated on A. You notice? In this case, for the posterior, the support is all concentrated in A. So that means that there's going to be some learning, but the learning is going to be for the wrong reasons because the agent is not taking into account what is happening in the true world. A less severe example of that situation is when you have a probability measure that excludes all the set A, whose support excludes all the set A of where the proposition is true. We will come back to the part B of this figure in a moment, but this is basically the motivation to define knowledge that we can acquire or that we can learn, but we can learn for the wrong reasons. So if we want to define knowledge, we have to take those things into account. So the definition of knowledge requires that there is learning and that the true word is in the support of the distribution or of the probability measure. And I'm going to say this first in words and then explain what it is and then the math is that the belief in the true word has increased with the posterior with respect to the prior. This is it. So how is this done? So remember that the definition of the support or an element being in the support of a distribution means that actually for any ball that I can put around it, I'm going to have a positive probability, a positive measure. So what I'm ensuring here is that in this part is that I'm going to define a ball which is centered at 0, at x0 in the true world, and with some radius epsilon. So then I'm making X a metric space because I'm defining a metric. And then what I'm saying is that for some epsilon, this logarithm of the posterior look at x0 is going to be bigger than the prior, than the belief of the prior, than the belief of the ignorant agents in the true world. So let me explain this again in more detail. Let's complete it. So what we're saying here is that the belief in this true world of the agent with additional information is bigger than the belief in the true world of the maximally ignorant agent in this case. And this has to be true only for some epsilon with strict inequality. Because if the strict inequality is not required here, then simply that can be 0 for all possible epsilons, and then we're and have no knowledge. Okay, so let me give an example, which is pretty cool. This is one of the areas that we are planning to develop more properly. You know, in bioinformatics, they have developed all these pipelines and they publish in systems biology all these papers with all these pipelines, step by step by step by step, and they make replication very difficult to follow. And replication is one of the big questions actually today in terms of reliability of AI and in part in terms of ethics too. So let's consider the following theoretical situation. Some researchers want to find the prevalence of the physical symptoms of a certain disease. So the space that we are going to consider is the space of the prevalence of the symptoms. So if the individuals in the population, what is the proportion of individuals in the population who present symptoms? That is given by a space given all the possible options, which I can describe as X, where X is X1, X2, it's a vector. And the space is 0, 1 squared. And this is for two labs. So this is the proportion of individuals with symptoms in lab 1, and this is the proportion of individuals with symptoms in lab B, lab 2. Now, the two labs belong to the same company set. And the company wants to find whether the estimates are consistent under some tolerance level, epsilon. So what we are going to obtain is that, well, X2, the proportion of individuals in symptoms for the second lab is obtained when the second lab tries to replicate the findings of the lab 1. So the proposition that we are interested on is that the second study replicates the first one. And then the truth function is going to be that the prevalences of the disease between the two groups are less than epsilon. So that the sets of words in which that is true is those pairs in which the condition is satisfied. Now let's say that X0 represents the actual prevalences of symptoms in the two cases. Notice that actually these two values can be different. The true values of prevalences between the two can be different, even, and you can even obtain that actually X01 and X02 do not belong to A. And this can happen if, for instance, the two labs consider different subpopulations. So let's consider first the situation in which lab 1 is totally transparent and gives all the information to lab 2. If lab 1 gives all the information to lab 2, nothing to hide, then lab 2 has all that it needs to replicate the result in the best possible way. So in that case, then we can assume that the discernment, the sigma fields, are actually, well, two Borel sigma algebras, the product of the two Borel sigma algebras for the product space. And then P2 is going to represent the probability measure obtained from the data, the complete data that they obtain. So that in particular, the probability of the P2 of the words in which the property is satisfied, the study is replicated, is just by definition the same. Now, when each lab uses all the data from all the individuals in this respective subpopulation, then what we obtain is that this P2 is just, again, Dirac delta measure evaluated at 0. So this measure is giving me exactly what is happening in the true world. Now, that's okay, but that is too topic, let's say. That almost never happens. One lab is not giving all the information to the other lab in almost any situation. So what happens usually is that when a second lab is trying to replicate the experiment from some first lab, They get only partial information. And if they get only partial information, then the second lab can only replicate things up to a precision delta. So that means that the space 0, 1 that I had originally can be partitioned basically in, or quantized in intervals of size of length delta. I'm assuming here that n is 1 over delta, just for simplicity example. So my discernment, my sigma field becomes then for the first lab, well, this the Borel sigma field, and for the second one is basically the sigma algebra that is induced, generated by this set, by this quantization of this state. So notice here then that there's going to be some lots of information, of course, for lab 2, because then this is not done. This is not the whole Borel sigma field. So the probability measure in this case then is given by P1, just like we defined the posterior, when for this G1, and this means that P1 is going to be P2 for all events that are in that sigma field, but outside the sigma field, between G1 and G2, we're going to have a lot of things that we don't know on the second part of the product. So this is not to, I'm putting this only for reference here, but the point what I want to show you with this probability here of replication in this case is that this is going to depend now on the length, on the tolerance that was defined for the replication epsilon, and then also on the precision level at which I can define now my second sigma field. So the posterior now here is not depending only on the tolerance as in the first part, but also on this sigma field. Also on this precision delta. That has a lot of implications because, for instance, this probability, the probability of replication is going to be always less than 1 whenever 2 epsilon is less than delta. That means, because what I'm going to have is that for some event, for some interval, let's say n delta and n plus 1 delta, what I'm going to have is that the tolerance is going to be contained here. So I'm going to have x0 minus epsilon, x0 plus epsilon inside this set. So I'm never going to be able to know precisely what is happening in that case, if this is the situation. So that's making that the probability of replication is always smaller than 1. So delta limits how much knowledge can be obtained from the two studies under incomplete information transfer. And since this is what is happening almost always, then replication is going to be more and more difficult. Notice here that we have only considered one step in the replication. Pipelines have several steps. In fact, following of those bioinformatics papers is kind of difficult because there are so many steps that I at least always become lost. And notice that this conclusion could not have been obtained just using Bayesian analysis. And the reason is that the first lab actually has an actual level of prevalence of individuals with the disease. So they have actually some probability, some proportion of individuals who have the disease in lab 1. That is not a Bayesian assumption. So that is not something that can be tackled by just a pure Bayesian analysis. This combination that we're making here of Bayesian and frequencies actually can solve that issue. Let me give a second example, which is closer to my heart at least. This is also related to a talk that I gave here for INSA last year in cosmological fine-tuning. Cosmological fine-tuning, in simple words, says that some of the constants of nature live in very narrow intervals, such that if the constant were outside of that interval, life, carbon-based life, would not exist in the universe. These are basically intervals that are set by physics in a very brute way. I mean, they say, for instance, that let's say, imagine one case, one famous case is the gravitational force, the gravitational constant. If the gravitational constant were bigger than a certain value, then the universe would have collapsed almost after the Big Bang immediately. And then stars would not have formed, and since carbon is forming stars, then we would not be here. On the other hand, if the if the gravitational constant were too small, then the universe would have expanded without stars forming again, and we would again not have carbon, so we would not be here. So that's the kind of reasoning that physicists use to define those intervals. But the point is that even with that kind of very brute reasoning, those intervals are usually very small. Now, the assessment and the point with physicists is that they usually think that because the interval is small, the probability is small. The problem, however, is that it's very difficult to determine what is the probability to use for some constant of nature, because what is beyond the universe to say what is the probability distribution that we're going to use. So in 2019, Fred Adams, a well-known astrophysicist, actually in a review paper acknowledged that to determine the probabilities it was still very difficult. I started to work in this problem like kind of at that time, and with my collaborators, we have produced already 4 papers in that direction. And we produce an algorithm, and this algorithm depends on what we're finding or what we are determining as a parameter space. What are the values that the parameter can take, the physical parameter can take. We give constraints in terms of moments, and then we have to input also the life permitting interval. So those things are done by physicists. The length of the life permitting interval is something that the physicist produces. How to calculate the probability is something that is more on the mathematical side. Now, what we do with this is then to find a family of maximum entropy distributions that satisfy these constraints. So for instance, we learned that the first moment is finite for some distributions on the space of non-negative real numbers, let's say. So then the maximum entropy distributions are going to be all the exponential distributions with some parameter, positive parameter. And then we estimate the probability of tuning by finding the maximum probability among all the collection of that interval. And if that probability is small, then the conclusion is that the variable of the constant of nature is fine-tuned, and if not, well, the procedure is inconclusive. That's basically the reasoning. Now, that's cool, but you know, physicists are kind of divided in the question, in the topic of if this is a valid scientific question. Max Tegmark from MIT says that it is a valid scientific question. He has a book called The Mathematical Universe, and he talks about it, and he says, well, this is a very cool this is a cool scientific question, we should pursue it, and he has actually written several papers trying to estimate those probabilities. On the other side, Sabine Hossenfelder, who is a very famous YouTuber physicist, has also a book called Lost in Math, in which he asserts that it is not a valid scientific question. So meaning that we cannot know if tuning is, if there is fine tuning or not. Well, in a paper that we just got published this year, together with the high school student that I was mentioning at the beginning, Alvin Matthew, we established the following principle. So our question is our answer is going to be a yes and no. It's some form of yes and no answer. So there is fine tuning of the parameter of some physical parameter when the constant can take only non-negative values. and the size of the life permitting interval is small relative to the value of the constant. I'm not going into the details, and if you want to see that whole talk, that is actually in the website of IMSA here. It's called on some aspects of cosmological fine-tuning. But let me give some examples of that situation. So for instance, for the Higgs vacuum expectation value, which is one of those constants of nature, they say that the value of the constant is this thing, which is of order 10 to the minus 17, and this is in units of mass Planck. Now the life permitting interval is this thing. And you see that the life permitting interval is of the same order of magnitude as the constant. So that the estimate of the probability under that method is almost 0.5. That is quite high to say that there is fine-tuning. On the other side, when we have, for instance, the critical density of the universe, the value of the constant is this thing. And notice that the interval is very small with respect to that value of the constant. It's actually of the order 10 to the minus 60. So that the probability estimator is going to be also of the same order. And the same thing happens for the gravitational force. And when we're taking the gravitational force, we take the ratio of the gravitational constant to the vacuum energy, which is from the vacuum energy, sorry, to the cosmological constant. And the cosmological constant is kind of a extreme example in physics because the difference basically between what we have in theory and what we have found in the experimentation is of order 10 to the 90. So the difference between what we know theoretically and we know in application is quite large. And that produces that anything that is compared basically to that cosmological constant gets, it's almost by definition has to be fine-tuning because how to close that interval of 10 to the 90 basically. So that ratio, for that ratio, the length of the interval is of order 10 to the minus 100, and then the estimator is in that case. So for these two cases, basically notice that these are two constants of nature that are non-negative and whose life permitting intervals are of very small order of magnitude related to the value of the constant. That is a big difference with this case in which, again, the value of the constant is of the same order as the life permitting of the length of the life permitting interval. So in this case, we use our framework of learning and knowledge to show that in these cases, when that condition is satisfied, again, when the constant takes on negative values and the size of the life permitting interval is small, then fine-tuning can be detected. If not, fine-tuning cannot be detected. Okay. So instead of explaining all these things, actually I want to make a natural extension in your minds that is kind of natural again. It is, if we define learning, learning can be seen as a process, actually, in which I am updating with more and more data how much I know about some proposition. And as I'm updating with more and more data, what I'm obtaining then is a sequence of sigma algebras, each contained an increasing sequence of sigma algebras, each containing the maximal sigma algebra that I had at the beginning. And the sigma algebras are associated with more and more data too. And the interpretation is the same that we gave from the beginning. The interpretation is that, well, we end up with probability spaces associated to each data set and to each sigma field that we have in the process with the same properties as we saw before. And in that case, then, the collection of pairs of data and the sigma field is referred to as the discernment and the data collection process. So we can define in this case a process of learning and a process of knowledge. In terms of the process of learning, we're going to call a strong learning when we have a sequence of probability measures associated to each of those measurable spaces, and data that is associated again to all of these probably respectively to each of those spaces. And the active information of the words in which the proposition is true is increasing, strictly increasing whenever the statement is true in the true word, or decreasing, strictly decreasing whenever the statement is false in the true word. And then in that case, we have a strong learning. Accordingly, we can extend the definition of knowledge in the same direction. So there is learning, there is a strong learning, and then the support each time has to be in those, the true word has to be in the support of those probability measures, and the belief in the true word has to increase with respect to that of the known person who knows those words. So we can do the same. Now, in the talks yesterday, Carlos and Ernesto made some interesting point, saying that, basically saying that this is too strong. That strong learning and strong knowledge are just too strong, because sometimes we need to take the tools, or sometimes just to, if you imagine data, we have to do. In the example that Ernesto was presenting yesterday with the Rubik's Cube, we have to generate some disorder again in order to produce some order. So in that sense, we could regard also what is happening with strong learning and with strong knowledge as too restrictive. So we can define something weaker that is, weak learning, just looking at what is happening at each point in time. But more interestingly, of course, we then can define what is happening asymptotically in the limit. And then in asymptotic learning, we have that basically the same definition can be developed, taking into account just in the numerator of the log, the lim-inf of the posterior probability at time k. Again, what is happening in the case of the ignorant person. Whenever the true word, the proposition is true in the true word, or that active information being negative for the lim sup in the numerator of the posterior, whenever the true word, whenever the statement is not true in the true word. Yeah, we can basically define knowledge in the same way. This actually is going to enable many interesting questions that we have now on relating this, for instance, to networks. Actually, just putting the kind of situation that I was talking in the beginning of, acquaintance knowledge and knowledge that. So how we have been studying some papers on how my opinion or my belief in a proposition is affected by the circle around it. So I can look at it from the perspective of networks. We can quantify that, and then we can see where those beliefs are going to in terms of the stationary distribution in the processing the network. That's basically it.
Thank you very much.
So in large language models of the transformers, does learning occur in this sense?
Oh.
And knowledge is
So yeah, that's a very good point. I forgot to mention that. So what we have realized basically is that in general in machine learning, just as the name comes, it's only focused on learning, and there's almost no focus on knowledge. So what is happening in the true world? So imagine that you are training your data, and you can train your data with respect to some parameters and some subset, and then your data is trained, but you can be looking at the trained data only at situations in which what is happening in the true world is actually excluded. And then you're going to, it's possible to learn, it's possible also not to learn, but it's possible to learn without getting to know what is actually the actual value. So you're not approximating in terms of knowledge, even though you can learn something, just that you're learning for the wrong reasons.
because you exclude the true world.
You exclude the true world. It's
Define-
possible to, it's a situation that actually happens a lot, and those pitfalls are famous.
And what's happening in the risk? So in the race minimization that is happening, that you have a population, the training population and the real population. Right?
Yes.
So you are not
So the training population is always a subset,
Yeah.
and that's always a risk, because you can take only some data
Really
around.
risk.
What we are referring here as counterfactuals, forgetting what is happening or just ignoring what is happening in the true world. So what is the true value of the parameter, and only looking at things that are outside.
So it means that you cannot generalize the parameters of training sample in machine learning for the real parameters or something like that?
Here. This is basically the situation. When you're training data, it's possible that you're training only this subset, forgetting what is happening, or maybe not taking into account what is happening here. All the machine learning is done basically in terms of learning, but not in terms of not in terms of knowledge, which requires that you have a bigger certainty with the data that you have acquired about what is happening in the true world.
And you can measure that.
Sorry?
You can generate a measurement.
Yeah, that's what the definition of knowledge does. This is what this is defined for. For instance, in the case of cosmological fine-tuning, we show that we can actually know that in the restricted cases that I was giving, then you can
Sorry.
know there is some.
Sorry, I have a question about it. So if you can measure, you can learn or not.
If you can measure, I mean, again, you can measure here the learning, but you're not going to obtain any knowledge about it if you're excluding this value. Because this value is always going to have probability 0. If this value is excluded from the support of your training data, you're not going to learn anything about this value, about that particular value. Okay?
So it means that what you're sampling is not representative of the.
It's not representative. It's not even including it in the one extreme case. And it's possible actually to include it and to get to believe that it's smaller in the true world than in the previous case, and in that case, then you're also not learning. So actually, what we're requiring is that in order to learn, your posterior belief in the true world also has to be stronger than the prior belief.
Going back to like the first one or two slides, 1 or 2 or something.
Okay.
Okay. Is there room to maybe the next one? Is there room to sort of recursively apply that to itself? Namely, that now we take statement 3.
Yeah.
And apply that to that statement.
Yeah.
So
yeah, we have.
we know that statement 3 is true, but is it justified?
Yes. So one of the things that I'm highly interested on is comparing these to both Turing's undecidability, which is recursive, and Deleuze's incompleteness, to see where can I establish some connections between the two. That's something that I want to see. If one implies, I would say that for sure this, and it's almost my hypothesis. I'm not pretending that I'm doing something stronger than Turing. That Turing implies that there's not going to Turing test is going to imply that there's not going to be any knowledge. For instance, that we cannot know. I'm almost sure that that's going to happen.
Yeah, and this constraint, you can know that something's true based on your models of the world today, right? Like what you have in your mind today. It may not be true based on your subset of that knowledge.
Exactly. So in that case, you're learning, but you're not acquiring knowledge. It's possible to learn without acquiring knowledge. So the idea of, that's a very Bayesian idea of we are improving our belief as we are acquiring more and more and more data. So that's one of the foundations of Bayesian of the Bayesian paradigm, in which as we are acquiring more data, we are perfecting our posteriors, and then we are using basically as more data is coming, the posterior that I had before becomes the prior of the next trial. So that's
interesting. That's in a way that's Jan LeCun's whole idea of knowledge, right? You gotta put in your mental models in there. If you don't really know. he's expanding on the notion of LLM when it comes to consciousness and knowledge based on the notion of mental models.
Mhm.
Right? That's what you're saying.
There is actually another area that you mentioned that in which I would love to apply this related to that part of networks. It is there is a biologist at Tufts University. I think that guy is going to win the Nobel Prize at some point. It's Michael Levine. He's also famous in all these podcasts about science and YouTube and all this kind of stuff. The guy is developing a theory of how, for instance, multicellular entities learn and know. And actually, I presented this for his group, Zoom talk. It's very cool to see how this can well represent how cells are learning as a group. Because among other things, one of the things he's doing is that he says that he sees cancer, for instance, as unicellular devolution of cellulars that behave multicellularly. So he says that suddenly some cell starts to behave again unicellularly, as in the past, as in the ancient past. And then other cells learn that and start to replicate that. So notice that this becomes like a network in which opinions are going from cell to cell too, and then they form beliefs and they start to act individually. And he has a very cool examples on salamanders and this kind of stuff of seeing how they restore parts and using that same idea. So I really want to develop in that. So,
Flatworms, right?
flatworms, yeah, yeah. So it's very cool. It's very cool. And this is one area where I would like to see that, just going in the same direction.
And there's a whole, I'm gonna very briefly talk about it already, but when we talk about capturing data, there's a whole belief that even though there's no nervous system and consciousness in plants, there's a whole belief that plants also learn and learn.
Oh yeah, that's right. Because
Yeah.
that's one of the things this guy has shown in some of those organisms.
Yeah.
So they don't have a.
So that's interesting because yeah, we'll talk about it.
They learn about it. It's very cool.
Yeah.
It's very cool, and I would like to expand also this theory into that direction.
Thank you very much.